The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Laboratories. I thought you were the principal.
No, that's my dad. That's number 3.
Okay. All right. Well, it's over to you.
Thank you, Charles. Hi, thanks. So yeah, I'm going to carry on with the testing, actually hit some of the same projects that Nick mentioned, more from the material side, the testing side. Just a quick outline of what I'm going to talk about real quick on flood testing. Just a little bit of highlighting on some of the intricacies of field testing and casting specimens for high strength. That's a whole separate presentation, but just essentially hitting that there are some differences, and then the strength and modulus testing, and then some examples again from Wanda, from essentially more towards the beginning of the project. Flood testing again, Chicago. That's Walt 1. I'm Walt 4. We've been at it since 1913. My grandfather, Walter number 2, worked with Material Service, which is now Prairie, when they were first developing the high-strength mixes back in the 60s and 70s. Field testing and casting. Air is key on the high-strength mixes, so a large focus has to be placed on air content. Most of them have de-airing packs in the mixes, through most of the time through the super plasticizer, but anything over 1% is just not going to work out in most of these mixes, especially the high modulus. They have to be really stiff. Most of the densities are up over 156, so your standard equation, assuming 145 or 150, just doesn't work. Any air is really going to affect, especially the stiffness. As Nick mentioned, most of these mixes are exceeding 8-inch slump. The exception is for puddling, which can be an issue because obviously you have to, how much of your deck has to be that higher mix if you have to puddle at a 28-inch spread. It ends up taking up half your deck. So that's definitely a challenge from the producer side, as well as just the quality control and understanding exactly where that mix is going when you're down at the pump, versus up on the deck. So again, we're typically running slump flow like it's as if it's SCC. Exclusively 4x8s, that's been true for many years. Typically, we are extending the cure. Instead of 24 to 48 hours, we're typically doing 48 to 72 hours. That's been recommended in 363 as well. A lot of those mixes will consolidate with a vibrator. They aren't very friendly for rotting or getting out of the wheelbarrow at all. So usually, we're casting with a vibrator, and they go immediately into a water bath. That's less for hydration. The mixes are so dense, I don't think you're getting a whole lot of water transfer. It's a lot more for that consistent temperature, consistent curing condition more than anything else. For compressive strength and preparation, we're generally grinding any of the high strength, especially the high modulus. You aren't allowed to use pads or caps over 7,000 unless you do some qualifications. And even then, you're never allowed to use them. And this is the kicker for specified over 12,000. Just to throw open a can of worms, I guess. There's a little bit of argument at ASTM right now about that part of the specification. It allows you to test on pads 12,000 specified concrete. Now, like Nick said, if we've got a 7 million requirement and it's only a 12,000 mix, which is true at Wanda, we're breaking at 20,000. How appropriate is it to use pads when you're breaking at 20,000 psi? I'd argue it's not, but at ASTM they'll just say, well, it's specified 12, that's what it is. So we grind anyway. Like I said, just to open up a can of worms. So here's an 8,000 mix. we hit 12, over 12. So, what is the specified isn't I don't think as big a deal as what is the reality. But moving on to modulus, again, it's being specified for stiffness, for narrow buildings. It's not an easy test to run, and there aren't a lot of labs that are actually able to do it, which, again, from the producer side is probably a little scary. There's only 39 labs in the entire U.S. that are approved to run the test. And that doesn't necessarily mean they run it any more than once every 2 years when CCRL comes through. Again, it's definitely something that needs to be considered when you're going that route. And in the development phase, usually the testing lab is hired about a week before the job starts. Hey, we're building a 40-story. You want to come out? Sure. They really need to be involved more on that early mixed development phase with that producer, so that everybody's on the same page. That's true from the producer standpoint too, because that the design that the producer puts into it really does depend on how well the testing is going to be done as well. They might have to produce 10% higher to account for a testing lab that isn't going to do as good a job. In Chicago, we have a nice limestone. It's really good for making high-strength concrete, compressive strength, but it's not very stiff. A granite basalt would be much nicer, much stiffer. As Nick said, we're usually well overproducing the strength in order to meet the high stiffness. So here's a typical modulus setup. Again, not measuring Poisson's ratio, just measuring the modulus. It'll spit out our modulus curve there. This particular specimen was loaded to 10,000. I think that's the ultimate strength of this. So it would have been loaded to 40% of that for the test. But currently, ACI 318 allows the use of the equations to determine your modulus. There's another equation. There's a 363 equation, which is a little bit different. Jim Cook put out an equation as well based on some testing he did in Texas. Bottom line, your individual stone is really going to be what dictates the mix, most likely, until you get into really high volume fractions of paste or something else can control. But generally, your coarse aggregate that you have locally is going to control, and you're going to have to rely on some lab testing if you really want to play around with the modulus rather than these equations, because the Cook equation definitely doesn't hold true for us in Chicago. 363 is conservative, so it undershoots. The 318 actually is unconservative and overshoots most of these high-strength mixes, at least for our stone. So it's definitely something to be careful of as an engineer. You can't just plug it into the equation and use it. In this case, plugging into those three equations, if you had a 12,000 psi compressive strength, put it in at 150 PCF, the three equations will spit out 6.6, 5.7, and 6.7 million for your modulus, which is a rather large range. So again, you really do need to measure. Way back in 1990, Jaime Marino, who was at, I believe, Prairie at the time, talked about this in an ACI paper about the different equations and the need to test to check. And that chart on the side is showing where the ACI equation is. There's an F dot equation compared to what the results were at different ages. So now into a little bit of a specific. Wanda Tower, which you saw with Nick, they were originally considering an 8 million PSI mix modulus requirement during development. What it meant is that on the lower floors where they had retail space, they'd be able to narrow up the columns by about 9 inches, which seems kind of crazy, especially in a place with as much space as Utah. But in Chicago, 9 inches of retail space on each column is thousands of dollars more rent. So it was a consideration. But then there isn't any guidance from 318 on modulus, not like there is for compressive strength. What do you do if it's a failure? Is that specified number an average or a minimum? Because realistically, the modulus is a bulk property for your whole building. It's how your building responds. So if you get one low for one column, does that really affect the properties of the building? And none of that's really established. So any of the engineers that are specifying modulus for their buildings kind of have to make this up as they go right now, and kind of figure things out. And again, that comes down to what can reliably be produced. You can make it in the lab in perfect conditions, but then how is it going to get screwed up? We've seen on the 150 Riverside job, they started adding water. The mix was like a 0.22 water cement ratio, and they were adding water at the pump, just hosing things down, just to keep things clean. You know, the pump operators have to keep things clean. And of course, that's a problem. And then again, how is it going to be tested? How is it going to be, those specimens going to be treated after they're cast? All that's going to affect what the properties that the client is essentially paying on. If it tests low, you can't really take a core of your high modulus column and try to test the modulus and figure out what it is in place. There really isn't a means to do that, and it's not going to test well. I thought I had pulled this out. So there was another project too, just an example of the different specifications. One Grant Park. This ended up a little bit different. Instead of testing every set like we are in Wanda, they settled for basically an average modulus specification, and then no single test less than 90%. That's what MKA's typically been doing on their specifications. But then rather than testing every set, we're testing every second floor for the first 10, where it really matters. Hopefully then we've established some kind of relationship, and then testing every fifth floor thereafter. So again, it's kind of no two projects are the same, even from the same engineer. So again, with Wanda trying for that 8 million, you kind of start to play with the limits of the material. So with Prairie, we did a bunch of testing. We're pushing. It was clear that there was so much variability at that upper end that we were limiting by some factor. So one of the things that we did is we went out direct to the quarries and cored some of the parent stone. That's one of the selected rocks there. But what that showed is it was actually really difficult to get an intact core due to the natural fissures in the material, some of the voids in the limestone. If any of those line up with the individual anchoring points on the modulus setup, you wouldn't get a very good result. So we actually had to take a lot of samples to get any data at all. But basically what it showed was it pretty much mirrored what our upper limit was on those lab mixes. So clearly the coarse aggregate, the local coarse aggregate, was our controlling factor. And you get to the point where how much more do you need to pay to ship in stone in order to get your 9 inches of space? So ultimately they did relax that requirement because it just didn't make economic sense. But here's one of the mixes, 12,000 used heavily at Wanda. Again, specified 12,000 psi, 7 million modulus at 91 days. Here's the kind of essentially field variability. So this is batch to batch, 193 batches. It ended up being pretty close together, especially considering it's multi-batch. Coefficient of variation of only 4%. A max just over 8, minimum 6.5, but all designed above that 7 million target enough to account for how they're going to possibly screw it up in the field, including my techs. But again, something to consider that I believe Bob mentioned, the compressive strength gain versus the modulus gain. I've got it down here at the bottom. Between 7 and 28 days, there's a 27% average strength gain for those 190 sets. 28 to 56 was 6%, 56 to 91 about 3%. The modulus is a lot flatter. And you can see that even more so when you test at early ages. For the production, every set, we aren't testing at the younger ages because we already have sets of 10. And doing more is expensive and bulky. But it's a much quicker gain at the start and then pretty much stays there. You don't get a whole lot going out over time. But you can see where that strength requirement is down at 12 versus the blue where it actually is. But again, most of the time your modulus is going to be controlled by your local course aggregate unless you start shipping in. And it's going to come down to your economics. And we're going to be putting an article together based on the variation there and some of the other projects, 150 Riverside, to try to help the engineers a little bit with that expected variation. ASTM has also done a round robin that Willie Morrison put together to try to refine the precision statement of the static modulus test. So that should be coming through hopefully relatively soon. That was really out of date and needed to be updated for the more modern mixes and size specimens. That's it.